Cell potential. So when we've been working on page 7 and looking at, if you look at the heading of page 7, it says reduction half potential, or half reaction, sorry. And that's because if it's a reduction half reaction, that is going to be which agent? The oxidizing agent. So the oxidizing agents start at the top left and work all their way down, and then reducing agents start at the bottom and get weaker as they go up. Are we good? All right. The numbers on the side, we haven't looked at them to this point, but they have an importance. The electric potential difference is the measure of the ability of the electrons to flow from the anode to the cathode. So yesterday we looked at voltaic cells and we drew a voltmeter and we put negative on one side and positive on the other side, and we showed the flow of electrons. That higher that electric potential difference is, the greater the electrons will move. The greater the electrons will move, the more what about the reaction? The more spontaneous, the more reactive, the more. Okay? We measure it in volts. Pay attention to units. A little m, capital V, is millivolts. A capital M, capital V, is megavolts. And it's called voltage. It's called electric potential. It's called potential difference. So when we see those words, those are code words for we are solving for V. The E naught symbol, E with the little 0 up at the top, indicates the electric potential being measured at standard conditions. So just like when we did gas laws and we had SATP, standard atmospheric temperature and pressure, versus STP, standard temperature and pressure, one was at 0 degrees and 100 millimeters of mercury, and the other one was at 25 degrees and 101.325 millimeters of mercury. Okay, there are similar conditions for electric potential standards. So some scientists a long time ago decided to see what are the electric potentials of each of these half reactions. And so that's why we have this standardized list in our booklet on page 7. Since a voltaic cell cannot work with only one half reaction, the reduction potentials for individual half reactions were recorded with hydrogen as being the other half reaction. And so, if I organize myself, you're on candid camera. If I look, 2 hydrogens plus 2 electrons will give us hydrogen gas. We will actually physically see bubbles forming at the electrode. If I look in the table on page 7, what is the voltage that's listed for this reaction? You're going to need your data booklets out. You won't get through this lesson without it. This one that we just wrote down. 0.00 volts. Okay? This is what we call a standard reduction potential. Okay? This reaction here is known as the reduction half reaction. So we're working left to right. So the hydrogen half cell has been assigned a value of 0. Everything in the data table that we work with on page 7 is in relation to this reduction half reaction. Okay? So we call it the standard, or we call it the reference cell. In order to figure out the standard potential cell, we can look at the cathode minus the anode. Always. It doesn't switch up. Hang on. Okay. You can't switch them. You can't change and do anode minus cathode. You also cannot change the sign. If it's listed, I thought I just got rid of that. If it's listed, are you girls okay? So you can never switch the order. It's always cathode minus anode, and you can never change the sign. So in Hess's law, if we flip the reaction, we change the sign. That doesn't happen in this situation. If it's plus 0.84 volts, it stays as plus 0.84 volts, okay? And we also don't multiply it by a coefficient to balance out anything. It is the number. That is what it is, okay? You have to be able to identify your oxidation half reaction, because you have to know that the oxidation half reaction occurs at the anode and the reduction half reaction occurs at the cathode. You have to know those pieces. Otherwise, you'd be like, I don't know what I'm doing with these numbers. Okay? If I was looking at a voltaic cell, this is going to be my strongest reducing agent. It's going to be the oxidation half reaction, and it's also going to be the most negative reduction potential. Okay. At the cathode, this is going to be my strongest oxidizing agent, which means that it must be my reduction half reaction, and it's the most positive reduction potential. Let's look at that. Let's see if they're telling us the truth. So if we open up to page 7, and we look at the infamous zinc versus copper reaction. Actually, let's just do this one. Here's the dichromate reaction. That's pretty common in chemistry literature. And here's the hydrogen reaction. Of these two, which one has the strongest oxidizing agent? The dichromate line. And so this is going to be our reduction potential, or reduction half reaction. And this is going to be our oxidation half reaction. When I go across, my reduction potential is plus 1.23 volts. And when I look at hydrogen going in this direction, right, because this is going to be my oxidation half reaction, it's minus, or it's 0. If I was looking at silver and magnesium, so I've got silver at plus 0.80. Actually, let's not do that. Let's use this one here. Silver and the sulfate ion, giving us H2SO3. Silver is higher than SO42 minus, plus 0.80, plus 0.17. This one here, the oxidizing agent, has the greater cell potential. Even though they're both positive, it's still larger. Okay? So they're telling us the truth. Let's work through these practice problems. It says calculate the standard electric potential for a voltaic cell. Voltaic cell is code word for spontaneous reaction. Spontaneous reaction means what? OA is greater than RA. Look at that. One word, two pieces of information. Calculate the standard electric potential for a voltaic cell that has copper and zinc as electrodes. So we've got copper solid. We would then have the copper ion. We would have zinc solid. And we would have zinc ion. That's what we would have in our solution. So then we go to page 7 and we start looking. I'm looking for copper, copper 2 plus, zinc, and zinc 2 plus. So I'm just going to start at the top. There's copper ion. And there's zinc ion. Okay? Which one is the stronger oxidizing agent? Copper. This is my strong oxidizing agent. Okay? So now I'm going to start at the bottom here, and I'm going to look for copper and zinc. There's zinc. And there's copper. Zinc is what? Okay, so now that I know those two pieces, where do I find my strongest oxidizing agent? Which electrode? Now that I know those pieces, now I can go back to my data booklet because I know that E naught is equal to E cathode minus E anode. Always. Doesn't change. And so I'm going to look at my cathode value. And I get negative 0. Cathode, Mrs. Pierre. I know. I was like, wait a minute. Plus 0.34. I have them backwards. Okay. I'm like, this does not make sense. So, oxidation at the anode. This is oxidation. This is reduction. That's at the cathode. All right. Now, we can start over again. So we see that copper is at plus 0.34. Then we're going to subtract, and our anode is our zinc solid, negative 0.76. I didn't. I put it inside the bracket. Okay? And so when I have positive 0.34 and I subtract negative 0.76, what does my cell potential end up being? 1.10 what? Volts. Okay? So this part here Even though I said, make sure you understand, I still went and messed it up. Never do more than more decimals than what's here. So 2 decimals max. Okay, and it because it's subtraction and addition, that follows that rule, right? You always go by the minimum number of decimals in subtraction and addition. However, cell potential is always written to 2 decimals. Calculate the standard cell potential for the voltaic cell in which the following reaction occurs. Let me tell you what the following reaction is. So we need to figure out what? We need to figure out which one's being oxidized and which one's being reduced.
So your 2I negative
Yeah.
is being oxidized through IHO.
Okay. Which means that this is the reducing agent. What else?
Your BR2 is being reduced from 0 to 8.
Which means that this is my oxidizing agent, right? So we know the oxidizing agent is the cathode and the reducing agent is the anode. So cell potential is cathode minus anode. So what is the cathode value? Positive or negative? What about the anode? How much? Positive or negative? So 1.07 minus 0.54, what am I going to get for a value? No guessing, you have a calculator. Okay, this is a standard cell. How does this go? Do we remember? What's on the left side of the salt bridge? What's on the right side of the salt bridge?
Cathode's on the right.
Okay, and it says that the E of the cell is positive 0.90 volts. It's asking us to find the cell potential of the gallium. So we know that E of the cell is equal to the cathode minus the anode. What's copper's value? So in order to solve for that, I'm just going to rearrange it. And yes, I left out the positives. That's a bad habit to get into because you'll forget. What do I get for a value here? Okay, that's the cell potential for gallium based on this particular reaction. Okay. Our reference half cell is now cadmium. So what is the standard reduction potential for calcium? Well, what is E naught for cadmium? Oh my goodness, why would they use such close words? What would the standard reduction potential be for calcium if cadmium is our reference, not hydrogen anymore? So what is cadmium cell potential? Look on page 7. Negative 0.40 volts. Okay, for it to be a standard cell potential, it's got to be to 0. So what do we have to do to go from negative 0.4 up to 0? Okay, so we're going to add 0.40 volts. So then what we're going to do is we're going to look at what is the cell potential currently based on hydrogen for calcium. Make sure you're looking at your data booklet so you know how this works. So you're going to look all the way down to the bottom to negative 0.287 volts. But now we're changing the standard reference cell potential. So we're going to go negative 2.87 volts, and we're going to add, because that's what we said we had to add, 0.40 volts. And so our new potential is going to be negative 2.47 volts. That's the new cell potential for calcium. What about if it was looking for silver? What's the cell potential for silver? Okay. So we're going to take 0.80 volts and we're going to add 0.40 volts. That is the new standard reduction potential for silver if we were reacting it against cadmium instead of hydrogen. Okay, what about if it was a calcium silver cell if cadmium was the reference cell? So cadmium is the reference cell. We have to add 0.4. When we do that, calcium was negative 2.47 volts and silver was plus, this is why signs are important, plus 1.20 volts. So how do we figure out cell potential? E cathode minus E anode. What do we have to do? We have to figure out the cathode and the anode. So we go back to here and we're going to look for calcium, calcium ion, silver, or silver ion. There's silver. And there's calcium way down at the bottom down here. So silver and calcium. Which one is the strongest oxidizing agent? Silver what? Silver solid or silver ion? Silver ion. So we have calcium, calcium 2 plus, silver, and silver plus. So this is our strongest oxidizing agent, which means then that what is our strongest reducing agent? Calcium is a solid, right? What am I doing? I'm writing it under the wrong thing. And this is going to be our strongest reducing agent. Okay. Where do we find the strongest oxidizing agent at? Cathode or anode? Where do we find it at? Cathode. And we find the reducing agent at the anode. Okay, so our cathode value is plus 1.20 volts, and our anode is negative 2.47 volts. What do we get for a value? Okay, that's an easy fix. So that. Part 4 says calculate the standard net potential for the calcium silver cell using the hydrogen half cell as the reference. So now we're going back to the original values in the data table that calcium and silver are. And we know that calcium is going to be negative 2.87 volts. And we know that silver is what? Okay. And silver is going to be plus 0.80 volts, correct? So cathode is silver or calcium? And anode is? What's my value? Eric's already figured it out. What is it? What do we see? It's relative because you're basing it on another half reaction. Because you have a standard reference value taken into account. Whether you use hydrogen's half cell or you use another one, everything becomes relative to that number. The reaction between calcium and silver is going to have a net potential of 3.67 volts. Okay?